Yeah, thanks a lot, and particularly thanks for staying to the end of the day, already after 6. So I want to present some results obtained in collaboration with Gianluca Calcagni and Daniela Riti on calculations of the spectral dimension on discrete quantum geometries and the dimensional flow we find there. So the general motivation here is to compute at all observables of geometry in quantum gravity approaches, which is important. It has two main goals. One is to characterize and check an effective continuum description of such geometries, and it's necessary to look at geometric observables to see whether a continuum limit really works. And on top, you expect from quantum geometries that on a small scale quantum regime, you get some corrections and thus new physics. So here, the topic is observables notions of effective dimension, which is in the first place simple because it's just a notion of the dimension of space or space-time. But on the other hand, it's already quite involved and basically what can be done so far. The relevant notions are the spectral dimension, the walk dimension, and the Hausdorff dimension, typically, which we have computed. But the focus here will be on the spectral dimension, as that's the observable which is most interesting. And though they are just notions of dimension in the first place, they are indicators for the kind of geometry one effectively gets. And as such, they turn out to be good tools to compare the content of theories as well. And altogether, these observables are indicator of a possible effective fractal structure according to this necessary condition for a geometry to be fractal. So, and a particular motivation to look at the spectral and the other dimensions is that in various approaches one has found a dimensional flow from a dimension from topological dimension on large length scales down to a smaller value, mostly 2, but in some cases also different smaller values at the Planck scale, so to say. And this is obtained in two complementary ways. It was first obtained in causal dynamical triangulations, via numerical simulations on these triangulations. And on the other hand, there are smooth approaches like functional renormalization group approach or Lifshitz gravity and non-commutative field theories, where the effect of a dimensional flow basically comes from a modified dispersion relation, which depends on scale. So here, we're interested in these dimensions in loop quantum gravity or related approaches like spin foams and group field theory. And there's a particular challenge if you look at the techniques, how to get these, how to compute these dimensions, because here quantum geometries, states of quantum geometry consist of a combination of combinatorial structures like graphs or complexes and algebraic data describing the geometry on top of those. So in some sense, often you can find a description of the Hilbert spaces as a direct sum over such combinatorial structures. That means a generic state in such a theory is a superposition of a complex with some data on top, and the sum is not only running over the labels, but it's also running over a vast class of combinatorial objects, typically. So in a previous work, we have already found out that for these dimensions, the combinatorial structure in these states is actually the more relevant one, the dominant one, compared to the data you put on top. In particular, we have recovered the continuum spatial dimension for semi-classical states and loop quantum gravity in a precise sense. And we found no larger effects even in the Planck scale regime, at least for single graphs, for states on a single graph. This is a bit in contrast to earlier heuristic arguments, where basically from the area spectrum in loop quantum gravity there was inferred a modified dispersion relation, then similar to the smooth approach as mentioned. So then you can proceed as there, and there was proposed a dimensional flow. This was not found in our more precise computation in this previous work. So the question here is there a dimensional flow to be found? And now we have found such a feature when we take large superpositions over the combinatorial structures into account. And even more, for a particular class of such a superposition, such a flow seems to be generic. So let me start by reminding you on what the spectral dimension is. It's defined, it captures geometry as tested by a test scalar field via its heat kernel, this object, which is basically the exponential of the Laplacian. And on a smooth manifold, you find an expansion around the flat solution here. And in the flat solution, you see that the heat kernel scales with minus d half. So this is the reason why you define the spectral dimension exactly as a scaling. You take the trace of the heat kernel to have a good definition. And then you can define a scale-dependent spectral dimension by keeping this diffusion parameter, diffusion scale, as an argument of this function. So simple examples to give you an expression, for example, is a torus, where you recover the topological dimension, and because of compactness, you get a fall off at larger scales. So the first step to do the calculation for spin networks or more general discrete geometries, discrete quantum geometries, is to have a notion of a Laplacian, which the spectral dimension relies on the combinatorial objects like complexes. So we have adapted discrete calculus to the framework of such discrete quantum geometries, and the crucial part here is that you take for a calculus, you take Stokes' theorem as a definition, such that you find that a field on a given p cell in a complex, the differential is just the field on the boundary, and on a combinatorial complex, this means it's a sum with some orientations over the field on the boundary cells. What we need for the spectral dimension is the dual scalar Laplacian, in the sense that you consider a field which sits on these knots which are dual to, for example, here in the triangulation, the triangles. And you find that the evaluation of the discrete Laplacian on a given knot is a sum over neighbors, the field on the neighbors, with some geometric quantities here, the volumes of the cells, the volumes of the boundaries of the cells, and dual lengths enter in this expression of Laplacian. And this is the full Laplacian which is used for all calculations. You can again use this, and in the discrete case, if you take, for example, torus triangulations, regular ones, lattices, you find a discreteness effect. So at the lattice scale of your discrete geometry, you get a fall off basically because there's nothing to resolve below the lattice scale. And if you then also have a torus and you have this compactness effect, you see immediately that to have a notion of dimension at all, you need sufficiently combinatorial large complexes to deal with to have a meaningful notion of dimension at all. So when you go now to quantum geometries, you simply take these volume factors in the Laplacian and promote them to quantum operators. and you define the quantum spectral dimension in terms of the expectation value of the heat trace. And if you calculate that through, you see that it basically depends on the expectation value of these Laplacian, discrete Laplacians now promoted to quantum operators. As said before, preliminary results on coherent states in LQG in 2+1 dimensions, where we can where we find that the quantum operator of the Laplacian can be effectively boils down to the discrete Laplacian as a the functional of the discrete Laplacian on length operators, which are well understood in this case. We set up a numerical setting where we can do computations on sufficiently large complexes, which is necessary, and do the calculations on various classes. And the basic result here is that we have good approximation to the classical geometries. Here you have all in one, so a discrete classical torus triangulation geometry, and here you see that the arrow to this, the difference of the quantum spectral dimension is only of order 10 to the minus 2. And in particular that the continuum spatial dimension is recovered in this case. And as said, that the combinatorial structure is more dominates in the sense that we have also calculated on other complexes, and it's always basically the discrete, the structure of the discrete geometries which is recovered. So what was not clear there is what happens if we superpose over complexes. Basically, because with the numerical methods, it was only possible to sum up to 40 of such complexes, and the results were not conclusive. So the idea in the work I want to present you here is to have some meaningful approximation based on the results in the precise case of the previous work, to model such states with a large number of complexes in the superposition. And these states can be interpreted as continuum states, as we take them at a fixed overall volume. And the assumptions are the following. The first is that the expectation value of the Laplacian is basically the discrete Laplacian, and a scaling factor which is derived from the spectra, the quantum spectra of some geometric observables in your theory. We take uniform geometries, so the quantum labels are the same on all cells. We restrict again to lattices with a given size n, and the fixed volume condition results in that the size of the lattice has to be adjusted according to the scale of the volume or geometric operators entering in this formula. So for the expectation value of a heat trace, we get a tractable formula based on analytic solutions of the lattice in the limit of large overall volume. And this allows to compute very large superpositions. So the results are that for spectra, which scale asymptotically as a power function, and for a particular class of states which are power functions, we get we find a dimensional flow to a value depending on these two parameters in the small scale regime. So we find a dimensional flow for such specific superpositions. So here you see that the topological dimension is recovered, and we find this plateau at smaller scales. And how much the plateau extends depends on the size of the superposition. So here we have up to 10 to the 5 complexes to be summed over in the superposition. In particular, according to the formula I showed you in the on the first slide, one can interpret one particular example of this class of states as a fractal, which is the one where the dimension goes down to a value of 1. And surprisingly, this is the case corresponding to the spectral dimension, space-time spectral dimension of 2 if you take the space-time dimension just as one dimension more than the spatial dimension. We find that there is no non-trivial effect for other classes of states, so superposition coefficients which are exponential or trigonometric. And you can extend this because only this power function behavior of the coefficients in the superposition is relevant. If you have different such scalings in various regimes of the states, you find even multiple plateaus. So in principle, you can construct states with all kinds of intermediate values of dimension. So to conclude, I've shown you how the quantum version of spectral dimension can be defined and remind you on preliminary results in 3D loop quantum gravity, which were in quite good agreement with classical geometries approximated. And I showed you in particular here the new result of a dimensional flow for superposition over a large number of graphs or complexes. And even though this is a very general model, it's tailored to apply to loop quantum gravity states, though in principle it's more general. It could also be used for example, states in quantum radical calculus. So, as an outlook, what could be done and what we are doing, what I'm doing is one thing is the question if there are any constraints from dynamics, as this is a very general model, and the details on the geometric data don't enter. The question for these superpositions is really if these from dynamics any constraints on the class of superpositions actually come in. Then to really compare with the other approaches would be good to directly calculate the spectral the effective dimensions on space-time. So in this case, on spin foams or sum over spin foams, possibly as described in GFT. And there's a recent class of spin foams, so to say, the cuboid spin foams, which might be a good example to test this, which I'm checking. And yeah, then what this all could be good for as well as there might be effects in cosmological applications of such a dimensional flow. And it would be interesting if for the particular states one has, which like GFT condensate states, which give cosmology, one can indeed find a particular dimensional flow and use the cosmological ideas in a precise setting. So thanks for your attention.
So to resume, you have two results, one for coherent states on a fixed combinatorial structure, right?
Yes.
So here coherent state means some kind of Gaussian on a single complex, or triangulation or cubulation or whatever.
Effectively, indeed, if you take the precise coherent states, it turns out that the phase is not very important. So in the end, it's indeed Gaussian kind
so
of
it's a Gaussian on a fixed complex.
Yes.
And there you see the dimensional reduction?
No, there you don't see it. On one complex, you don't see any particular results.
So it really behaves classically, let's say.
It really approximates the dimension of the classical geometry approximated. Yeah.
So even if the time is flowing, it stays the dimension stays the topological dimension essentially. The spectral dimension coincide with the topological dimension.
Yeah. So the classical geometries peaked on for a single complex.
Yes.
They are already discrete geometries. So for this reason, you have already discreteness effects and compactness effects. So you have to zoom in on this meaningful regime, but there you indeed recover the topological dimension.
Okay, and in the second case, instead you give up those Gaussians, and you just consider superposition now of complexes.
I approximate the Gaussians because I've already seen that the Gaussians are very similar to just the single discrete states.
Okay.
I leave the Gaussians here out, but in principle this applies to the Gaussians as well.
And now superposition means what? On a fixed graph, a kind of refinement of the same graph, or so now it's superposition over complexes. But what do you mean with this?
The assumptions are the relevant assumption here is that we're summing over lattices, and the lattices are a fixed volume in the sense that we take the lattice of a size according to the geometric to the spectrum for the given state, such that the overall volume is fixed. In that sense, it's either a refinement or yeah.
So the label of the states is the number of cells essentially, and you increase this number of cells, and then you sum over it, and here what. And then you give up the Gaussian because you said, okay, I already have seen that on a single cell the Gaussian is not relevant. Yeah. It's more or less classical. And what you see now?
Now you see that I mean, in these states still it's a so we have fixed the class of combinatorial structures to be summed over, right?
Mm-hmm.
And induced, I mean, motivated by the Gaussians, where we see that a given quantum number is well approximated. We sum only over one quantum number uniformly on all. So there's still this superposition coefficient, and if the superposition coefficient has a power function scaling, then we find a flow to a value which depends on the scaling here, and on the spectrum. So
and those are not the effect of the previous kind, discretization.
These, yeah. So I mean, you still see here. You still have on the smallest member in the sum. This contributes still the discreteness effect, and you even see at the largest scale. I mean the compactness scale would is in principle there as well, but as we take the limit of large over a volume, this is not there anymore. So in principle, these effects are still there, but in the intermediate meaningful regime of dimension, you find this flow with the different values.
The final message, sorry for the many questions, but I'm very interested, is that you don't see quantum effects.
So this
in this flow,
I would call this a quantum effect, since this is an effect which stems from a particular kind of superposition. So it classically doesn't make sense to consider. I mean, there is no sense of a sum of complexes. But in the quantum theory, you know that the Hilbert space contains states on all kinds of graphs or so, and this superposition quantum effect feature gives you this effect. It's not there otherwise. So I would call it a quantum effect.
Okay, thank you.
It's just the first talk I hear here about the dimensional reduction, but you stressed strongly observables of a space-time, and among these the spectral dimension. Now, if you if you're really thinking of a space-time and you define a spectral dimension via Euclideanization and all that procedure, is that truly, did you mean observable in a physicist sense, or is it some other sense? But it's not a question to you, actually, to anybody here. It's an aspect of discomfort for me that we call these things observables, but I don't know how in principle I could measure it.
I call it an observable in the sense of an operator in the quantum theory. Not in the sense that the expectation values of this operator, I have a definite idea how to measure it in the sky. No, this as I'm doing here computations only on the spatial states.
Yes, I know.
This doesn't.
Yeah, no, but I'm asking about the space-time case, which is of course perhaps more. I mean, this is
so from this perspective,
work,
in these approaches, typically the question of Euclidean or Lorentzian geometry basically enters exactly the geometric data you put on top of these structures. So this model is kind of independent of these ingredients, because it depends really on the combinatorial structures entering the theory. Yeah, so actually, in this, the plots I show you here is actually hypercubic. Though you can easily extend it. So if you compare the various kinds of regular lattices, be it simplicial or hypercubic or something octagonal or hexagonal or so, there's not much difference. So this should be universal. Yeah, should extend to. Yeah. No, from this perspective, not at all.
Maybe going back to this question of classical versus quantum, have you tried to do maybe the same kind of calculation, but with rather than using these states, using the density matrix, which is diagonal? So in other words, equivalent to this, but with off-diagonal elements neglected.
So I'm not quite sure in what sense you expect this to be different from such states and the expectation value as obtained here.
So it's the same formula, I guess, no?
Yeah, for
this particular observable.
I would expect that, yes.
Okay, if there are no more questions, let's thank the speaker again. And this concludes our session for